Welcome. So this is 48G Tape 2, and I'm showing you this first slide again just to remind ourselves that we're in the process of looking at equilibrium, that is sometimes called statics, where the sum of the forces add up to be zero vectorially. And later on we'll do the non-equilibrium, the so-called dynamics, where when we sum the forces acting on an object, we'll find that there is an acceleration which is non-zero. And last time we looked at this example in three different ways. There was vectorially using a diagram, there was using trigonometry using horizontal and vertical axes, two equations needed for two unknowns, and then there was picking a new axis which would enable us to ignore, in last time's case, t right. So we could solve it with one equation. A cleverer geometry enabled us to do simpler trigonometry. We're going to continue with this practice, and I'm going to do trigonometry mainly, and we're going to basically look at some other examples that come out of this field. So here's an example. Let's get a black pen and let's have a look at this. When you're drawing diagrams, try to make the angles look realistic. So if this is 30 degrees, try to make it look like 30 degrees. And then make your object relatively small. It's a 2 kilogram block, so I put 2 kilograms inside it. And then the next thing is put your thinking hat on and figure out what forces have not been mentioned. It says a 2 kilogram block is stationary on an inclined frictional surface. What is its normal force? Well, the normal force I know is Fn, and I know it's always perpendicular to the surface. What other forces are on here? Well, there's got to be a weight, so that would be Fg. And that would equal 20 newtons. I know that because 2 kilograms in a force field of 10 newtons per kilogram gives me 20 newtons. Now, is that all the forces? It says it's a frictional surface. There's a clue. Frictional surface. There's going to be a force due to friction, Ff. And I know that is going to be up the slope, because if for no other reason then, vectorially, if I add Fn and Fg together, I get a force down the slope, and if that's not balanced by something, I'm going to get an acceleration down the slope which is going to change my velocity. And this says it's stationary, so it's steadily at 0 meters per second. So there's my three forces. Now let's just remind ourselves. I could then draw myself a scale diagram. I could say there's my weight, and here's my Ff at 20 degrees, and then here's my Fn, and I actually know that these two are at 90 degrees to each other. I know that this is 30 degrees. I know that this must be 30 degrees from the geometry. I can then say, well, that is the length of my Ff, and that is the length of my Fn, and I can use the scale. If I had 5 centimeters for every newton, if I had 5 newtons for every centimeter, so that this was 4 newtons long, I'd measure how long this was, and I'd work it out. Then the other clear way of doing it is to do it using trigonometry. And in a test I'd say using trigonometry or using a vector diagram. But if I was doing trigonometry, then what I would do is I'd have two choices. I could do a horizontal axis and a vertical axis. I'd have two equations and two unknowns, and that would work, but it would not be the most efficient way to solve this. The most efficient way to solve this is to say, I don't want to find FF. And so I am going to construct an axis which is perpendicular to FF. That's going to be perpendicular. FF has no component on the green line. Fn does. Fn is along the green line. It is all component. And Fg does have a component along the green line. I've got to be able to draw this well. Sometimes I'll see students who don't draw their diagrams and so they make mistakes. It's important always to remember that the original vector, in this case the 20 newtons, is the hypotenuse of this right angle triangle. And then, having seen that, I know if this angle down here is 30, that means that is 60. Can you see how it's a little angle and a big angle? And this is another little angle, so I know that's 30. And so this is the big angle, so I know it's 60. Can you see how when you have little angles and big angles, you can recognize them? But if all your angles were 45 degrees, you'd get confused. So then I have a choice. I can say that this is 20 cosine 30. Or I could have said it was 20 sine 60. It's the same thing. I like to put a little circle around that. There's one of my components along this axis. And then this other component is actually Fn itself. I'll draw it in red so that we recognize these are the two components. So the FF is not involved because it has no component along the green line, and I found the component of the FG along the green line, and I've effectively found the component of the Fn along the green line, so I'm complete. I have to decide which end shall I make positive and which end shall I make negative. It does not matter as long as you are consistent within a problem. You can't change your mind halfway through the problem. Now, this object is not accelerating at all. It's stationary. And that means that the sum of the forces along any axis through the object equals 0. I chose to do the green axis because it had the advantage of enabling me to ignore FF. But I could use any axis. Wouldn't have been as easy to solve. I might need two axes because I have two unknowns. But any axis I could apply this equation to because it is a statics problem. So I'm going to say sum of the forces green line. And so I look at my diagram and I say plus Fn added to minus 20 cos 30 equals 0. So, rearranging, Fn is equal to 20 cosine 30. So Fn is equal to 17.32. Newtons. And there it is, 17.32 newtons. So let's step back for a second. So first of all, recognize you get very little verbal information in this kind of problem. You gotta draw a diagram. You're not even told all of the forces that you have to deal with. So you have to get comfortable enough with this that it's not a surprise to you that there's a weight that you have to take into account, and it's not a surprise to you that there's a frictional force you have to take into account, and you know the direction these things follow. And then you have a decision to make, and that is, will I do this with a two-equation method where I take a horizontal component and a vertical component? I have two equations with two unknowns. Or do I act more strategically and say, I don't want FF in this problem, so I'm going to construct my axis. You always resolve forces along an axis. The sum of the forces equals 0, or the sum of the forces equals MA applies to an axis. So I could be more strategic and say, I'm going to construct an axis which will enable me to ignore FF in this case. And then I construct it. I need a bit more geometry, but I can do that with a good diagram, and I can solve it relatively easily. That's the way I'd recommend. So let's try this second problem. And here again, I'm going to try and draw my diagram well. Again, if it says 30 degrees, make it look like 30 degrees. A small block, just big enough to get the mass inside it. And it's asking, in this case, it says a 2 kilogram block is stationary on an inclined rough surface. What is its frictional force? So now I kind of tell you there's a frictional force. But what I didn't tell you is that, well, yeah, there's also a weight, and that's going to be 20 newtons. And there's also going to be a normal force. And I don't know what that is. I could do a scaled vector diagram. I could draw, say, 5 newtons for my 5 centimeters, so 5, 10, 15, 20 newtons. And then I draw my axis up here that's at 30 degrees to the horizontal. And then, because I know this is at 30 degrees to the vertical, I draw an axis down here where that's 30 degrees to the vertical. These cross at 90 degrees. I know that my FF must have gone in that direction, and I know that my FN goes in this direction, and I could use the same scale to measure whichever one of these I wanted. I can do it graphically, and in a test I might say use the method of scaled vector diagram to find. But on this one, I want to find the frictional force, so I want to get rid of the normal force. And so I'm going to draw an axis which is perpendicular to the thing I want to get rid of, which is this normal force. And I say, oh, the sum of the forces along the green line equals 0. And I go back to my diagram and I say, oh well, this FF is actually along the green line, so it is its own component. But this 20 newtons is at an angle. And again, you've got to be able to draw it confidently and correctly. This approaches the green line at 90 degrees. And I can say that this is going to be 20. Well, this is clearly the small angle, so it's 30. If this is 30, then that's 60. If this is 30, then that's 60. And if that's 60, that's 30. I can go little angle, they're both going to be 30 degrees. And I can say that this component, this red component, is going to be the hypotenuse, which is 20, sine 30. I could have said 20 cosine 60. It's the same value. And then the next thing is I got to know, is that a positive end or a negative end? It's up to me. I can name it. There's my positive and there's my negative. And then I say, let's write down an equation. So I'm going to say the sum of the forces along the green line equals 0. So plus FF, sum means added to, minus 20 sine 30. Can you see how the negative, the red vector is pointing in the negative direction? And these added together equals 0. Rearrange, FF is equal to 20 sine 30. So FF is equal to, I know the answer to this one, 20 sine 30, and it's going to be 10 newtons on that one. 10 newtons. Now, I'm sure there are some people who are saying, oh, he put the green axis along the same direction as the thing that he wanted. And in this case, that happens to be true. But the actual fact is, I put the green axis at 90 degrees to the thing that I didn't want. And that will always be true. So watch out for trying to do shortcuts on my shortcuts. I'm already giving you the shortcut version. Let's look at this next one. A horizontal applied force of 8 Newton causes a block to slide at a steady speed of 7 meters per second across a table. So 2 kilograms. I like to put my forces as pulling forces, so that's going to be 8 newtons, and it equals, I'm going to call it FA for F applied, and it causes it to slide at a steady speed of 7 meters per second. What is the coefficient of kinetic friction between the block and the table? Oh my word, that was came out of nowhere. So I want to find my mu k, and well, let's look at my diagram. Is my diagram complete? And I can say, well, no, because there's going to be an Fg, a weight, which equals 20 newtons. And in this case, there's going to be a normal force. And I can see by symmetry that that's also going to be 20 newtons. If you like, the sum of the forces vertically is equal to 0, so minus 20 added to plus 20 equals 0. But there's also going to be a frictional force. And for this, I am going to probably need both of those. If I take this mu k, I can say, well, the linking equation is FF is equal to mu k times Fn. So mu k is equal to FF over Fn. Okay. So what do? I say find Fn using the sum of the forces. I'd like to ignore FF, so I'm going to draw a line vertically. The sum of the forces vertically is equal to 0, and so I can say plus Fn, let's make this positive up here and negative down there, plus Fn added to minus 20 is equal to 0. So Fn is equal to 20 newtons. And then I can say find Ff using, I want to ignore my Fn, and so I draw a line horizontally. The sum of the forces horizontal is equal to 0. I say plus well, let's write it down. Plus Fa added to minus Fn is equal to 0. Let's have a look. I know what Fa is. Plus 8 added to minus Fn is equal to 0. If only... sorry. Bang! So I resolve my forces horizontally, and I say plus Fa added to minus Ff is in the negative direction, is equal to 0. And I know what Fa is. Fa is 8, so it's plus 8 added to minus Ff is equal to 0. And I want to find Ff. So Ff is equal to 8 newtons. So the final step is to go back to the beginning and say mu k is equal to Ff over Fn, which equals 8 over 20, which equals 0.4. And there are no units for the coefficient of friction. So there we have it. I used a good diagram. I tried to solve in one step. Philosophically, I tried to solve here, and I realized, oh, I need to find these two things to solve it. And then I said, well, how can I solve Fn? And I figured out how to do that. And then I said, well, how do I solve Ff? And I did that, and then I substituted my answers back in. Notice I've written down enough that I can easily check my work. The way I'd check this at the end of the test is I would say, oh, I think the answer is 0.4. Where did that come from? Well, that's 8 over 20. Well, that's right. Well, where did this 8 come from? The 8 came from here, which was plus 8 minus Ff. Oh, that makes sense. Where did this 20 come from? Oh, the 20 came from here. I can check that mathematics. And why do I want to do this? Oh yeah, the basic equation. So I've written down enough that I can go through it step by step and check it. And it makes life much easier when you do that. Let's look at this next problem. A 3 kilogram block is stationary but on the point of slipping. What is the coefficient of static friction of the inclined block? So 20 degrees. 20 degrees. And it's a 3 kilogram block. So that means that that's going to be 30. And there's always going to be a normal force. And there must be a frictional force to stop this thing from sliding down the incline. Is there applied force? There's no mention of any applied force. So those are the three forces that I am dealing with. And I say, how can I find the coefficient of static friction? I say Ff is less than or equal to mu static times Fn, and it's on the point of slipping, so Ff is equal to mu static times Fn when you're on the point of slipping. Mu s is equal to Ff over Fn. Didn't we do a problem just like this? We did, but the diagram was very different last time. It was moving, it was a moving system, but it was not accelerating, so it was still a statics problem even though it was moving. It was in equilibrium. Whereas this one is stationary, but this one's on an inclined plane. So what I do is I say, okay, let's find Fn using the sum of the forces. I want to ignore Ff. I want to be perpendicular to the plane. Sum of the forces perpendicular to the slope, or if you like the green line, equals 0. Now I'm getting more practiced. There's my component, and I know that this is going to be 30 cosine 20. If this little angle here is 20, the little angle there is 20. So that's 30 cosine 20. And this force up here is Fn, and Ff has nothing to do with this axis. So we say, let's call this a positive end, let's call this a negative end, plus Fn added to minus 30 cos 20 is equal to 0. So Fn is equal to 30 cosine 20 newtons. I'm going to leave it like that because I want to show you something in a few minutes. What do I do about the other axis, the other parameter? Find Ff using the sum of the forces parallel to the slope. I'm going to have an axis going in that direction because I want to ignore Fn equals 0. Again, I'm going to draw my component in. My component is like that, and I say it's 30 sine 20. And make this the positive end if you like, and make this the negative end. And I say plus Ff added to minus 30 sine 20 is equal to 0. So Ff is equal to 30 sine 20. Now I go back and I say mu s, my coefficient of static friction, which equals Ff over Fn, is equal to, and I look on here and I say, oh, that's going to be 30 sine 20 over 30 cosine 20, which equals, can you see how the 30s cancel, and I have a sine 20 over a cosine 20, an opposite over the hypotenuse divided by the adjacent over the hypotenuse, which gives me an opposite over an adjacent, which equals tan 20. So this equals, I get my calculator and I go tangent of 20 which equals 0.36. 0.36. There's my answer. And it's a kind of nice way that you can work out the coefficient of static friction for a block or a book on a surface. You just tilt it and you measure the angle at which the object starts slipping, and the tangent of the angle is your coefficient of static friction. It's kind of nice. You need not have known to do this. You could have worked out 30 cosine 20 as a numerical value, and you could have worked out 30 sine 20 as a numerical value, and then you could have just divided one by the other. There's no reason to do that bit where you did that little trigonometric manipulation at the end. It's just it's interesting to recognize that that's possible. Can you see my approach is the same every time? I read the words and I draw a diagram, and then I say what's missing, and I figure out the forces that are not mentioned and the angles, and I try to draw it reasonably well. I try to solve the problem in one step. I always say, what do I want to find? Oh, mu s. Let's try and find mu s. And I'm not surprised when I don't have numerical values to put in. That's just telling me it's a 2 or 3 step problem. And then, given that I need to find ff, I say, how can I find ff? And it's resolving forces. It's just I've got 2 forces, I've got 2 unknowns. Let's pick an axis where I can ignore the unknown that I don't want. I apply to find Fn the same principle that I apply to Ff. And the rest is sums, really. It's the diagram and the thinking through it that's the physics bit. And if you practice, you get to the stage where I can show you an example you've never seen before and you can approach it. Because you learn the approach. There's no point in learning this problem, because I doubt I'll ever ask you it again. I'll ask you a problem with similar skills, but I won't ask you the same problem again. So don't learn the problem, learn the approach. Keep asking yourself, why did he do that? How did he know to do that? And if you don't know how I know to do something, that's when you ask a question. So there we have it.